At the end of the 20th century, the 100 most prominent physicists were surveyed. Just behind Einstein and Newton, Scottish physicist James Clerk Maxwell was voted the third greatest physicist of all time. Unfortunately, compared to Einstein and Newton, Maxwell is so less known. Einstein described Maxwell's work as the most profound and the most fruitful that physics has experienced since the time of Newton. Maxwell is probably the greatest scientist of the 19th century, just behind Charles Darwin. His main contribution is mathematically unifying the theory of electromagnetism into such a coherent framework that can even fit in your t-shirt. Modern technology, such as communications and electronics, derives directly from his equations. But the ultimate importance of Maxwell's theory is that it is the prototype for all the great triumphs of 20th century physics. Maxwell's approach was surprisingly modest, drawing inspiration from his old colleague Faraday and everyday mundane concepts such as water flow and vortex motion. In this video, we'll follow his remarkable yet brief career. Maxwell was born on the 13th of June 1831 in Edinburgh, Scotland, as the only child of his parents. However, he grew up at Glenlair as a country boy. Maxwell lived for most of his life in the Glenlair house, where he wrote some of his classic papers. James was a quiet child, likely due to his mother's early death when he was 8. His protective father chose homeschooling, but the tutor's harsh punishments made it a year of torment. Eventually, his father sent him to the prestigious Edinburgh Academy. Surprisingly, only at 14, he published his first scientific paper on the types of curves one could draw using pieces of thread. As a promising young mathematician, Maxwell travelled to Cambridge University. At Cambridge, he joined the elite secret society known as the Cambridge Apostles. Maxwell was actually a devout Christian throughout his life, and spoke of his faith in many of his letters. He even used the arguments from the beauty of the Trinity while discovering his equations. Sadly, while at Cambridge, he lost his father as well. It is often speculated that his strong Christian faith might have been due to the loss of his loving parents at such a young age. Maxwell eventually left Cambridge for a new vacant professorship position at Marischal College, Aberdeen. By this time, he was only 25 years old, much younger than any other professor. Maxwell's first major work, on the stability of Saturn's rings, established him as a serious mathematician by age 25. This was mainly because the problem had been selected as the subject of the newly announced Adams Prize. The challenge was to explain how such a strange structure could be stable and not break up into pieces. This problem had puzzled astronomers for 200 years, even the great Laplace. Maxwell explored the three possible structures. 1. A non-uniform solid ring. 2. A fluid structure. Or 3. A collection of countless separate particles. Using Fourier analysis techniques, Maxwell showed that solid rings and fluid rings would not be stable and would inevitably break up into separate blobs. Thus, by elimination, he showed that although the rings appear to us as continuous, they must consist of many separate bodies orbiting independently. His submission earned him the Adams Prize. As it turned out, his was the only entry. The judge for the prize was Astronomer Royal Sir George Airy, who praised Maxwell's work as one of the most remarkable applications of mathematics to physics that I have ever seen. The most interesting fact is that he relied on mechanical models to develop his insights, a theme that repeats again and again in his work. He designed and built a hand-cranked mechanical model of Saturn's ring, which is now housed at the Cavendish Laboratory in Cambridge and remains accessible to visitors. In all, this work earned Maxwell, just at the age of 25, recognition from Britain's top physicists. He was now treated as an equal by such men as Stokes and Lord Kelvin. Maxwell's theory of electromagnetic radiation was undoubtedly his most significant contribution. The ultimate importance of the Maxwell theory is far greater than unifying electricity and magnetism. Its ultimate importance is that it is the prototype for all the great triumphs of 20th century physics, from relativity and quantum mechanics to standard models.
It was light. So without time, it looked at first like there were many things, motion and gravity, electricity and magnetism later, and light. But when Maxwell put together the laws of electricity and magnetism, he found out that the behavior, that the equations that he had produced expectation that would be behavior of waves that would propagate at a speed, which was figured out from electrical measurements, but came out the same as the speed that light actually propagated. And so there was a new theory of light, which is that it was an electromagnetic wave, and Maxwell's great synthesis in 1873 was to connect electricity, magnetism, and light. Light is just one aspect of the electromagnetic wave, which can have different kinds of wavelengths from that point of view. And if you have different wavelengths, if the wavelength is very short, between about 400 millionths of a meter, no, the centimeter, 400 millionths of a centimeter and 700 millionths of a centimeter, then you see it directly with the eye. But if it gets longer, the wave is, well, it's a long end, it's red, and then the other end, it's blue. And if it gets longer than the red, we call it infrared. The rays are there, but the eye doesn't see them. The pit viper has an eye that sees the infrared. And if you go in the other direction, into beyond the violet, then we can't see it again, but the bee has an eye that sees the ultraviolet. And if we go still further to the far ultraviolet, no animal has it that can see it, but we can make instruments that detect it, or photographic plates, and so on, up into X-rays and so forth. And down in the other direction, far infrared, you get into radio waves, and we can build instruments that detect them, and we can use them to advertise soap. In addition, so that is an enormous range of one property, the wavelength. A range of phenomena that's a complete, enormous spectrum. The spectrum we see with the eye is a very narrow range, and it's the entire spectrum. It's all put together with the one theory of electromagnetic waves.
It took Maxwell over 10 years and multiple papers to shape those equations in these final forms. The main difficulty was that Faraday's field concept was extremely hard to grasp because fields are intangible by nature. Maxwell thus had to rely on analogies and mechanical models, which might seem bizarre and outlandish from a modern perspective. At the time of Maxwell, 4 key experimental discoveries showed that electricity and magnetism are closely related. The first 2 were electromagnetostatics, first discovered by French engineer and physicist Coulomb. Third was the magnetic effects of electric current as discovered by Ørsted. And the last was the electromagnetic induction discovered by Faraday himself. Then, it was globally accepted that the phenomenon of electricity and magnetism must be unified. The leading approach was proposed by the French physicist Ampère, who Maxwell referred to as the Newton of electricity. This was a fitting title because, in Ampère's and Newton's approaches, one object's motion can be affected by another object even without the two being in physical contact. Faraday, however, came out completely opposite. He proposed that electromagnetic interactions occur through fields, rather than direct action at a distance. These fields exist in the space around magnets and electric currents, mediating the interactions. However, the majority of scientists, especially outside Britain, had failed to realize its significance, mainly because Faraday's work lacked rigorous mathematics. Ampère's work, in contrast, was mathematically sound. Then, it was left to followers of Faraday, particularly Kelvin and Maxwell, to formalize his field-based approach. Maxwell brought to this task skills, insights, and attitudes that had developed through his education at Edinburgh and Cambridge. Before doing any mathematics, Maxwell first decided to understand Faraday's work and intuition, a decision that proved very fruitful. Faraday had inspired Maxwell to think of electricity and magnetism in terms of field lines, just like water flow. There are 2 key concepts, divergences and flux, used in fluid dynamics. Divergence at any given point is a measure of how fluid spreads out or comes together at that point. Curl, as the name suggests, measures the rotation or twistness of a fluid at any given point. The first paper Maxwell wrote on electromagnetism was titled On Faraday's Lines of Force, published in 1855. Merely as an analogy, Maxwell proposed that electric and magnetic fields could be thought of as incompressible fluids. A key property of an incompressible fluid is that its divergence is zero. This allowed Maxwell to immediately write down the mathematical expression for the behavior of magnetic fields. The divergence of the magnetic field is zero. This is the first Maxwell equation. The interpretation is that, unlike electric fields, there are no positive or negative magnetic charges that could act as a source or sink. Magnetic poles always come as a pair. Since the electric field has positive and negative charges that can act as a source or sink, the divergence of the electric field is equal to the charge density. This is the second Maxwell equation. These two equations are also called Gauss's law for electric and magnetic fields, though Lagrange was the one who first wrote it. The main limitation of this fluid analogy was its inability to explain the interactions between electric and magnetic fields. It took him another 5 years, along with insights from another great scientist, Lord Kelvin. Kelvin was an advocate of the vortex theory of the atom, which hypothesized that an atom was a vortex in the ether that pervades space. Kelvin suggested that these rotating vortices could serve as a model of a magnetic field. Maxwell found Kelvin's approach particularly attractive and took it seriously, though it might seem bizarre from today's perspective. He began with a model in which the whole space was filled with a vortex tube whose velocity represented the strength of the magnetic field. But there was an immediate problem. These rotating vortex tubes would experience friction, causing them to lose energy. Maxwell adopted a practical solution by inserting ball bearings between the vortices, which he identified as electric particles. When these ball bearings are free to move, they carry an electric current. In conductors, these electric particles are free to move, whereas in insulators, they are fixed. In 1861, he published a paper titled On Physical Lines of Force, with these mechanical models. In that paper, he had a slightly different version where hexagons represent the vortices. The ball bearings are current-carrying particles. Remarkably, this model could explain all known phenomena of electromagnetism. In this diagram, the change in the speed of the vortices corresponds to the change in the strength of the magnetic field. This would cause the ball bearings to rotate in response to the changing speeds of the adjacent vortices. Since rotation corresponds to the curl, we get the third Maxwell's equations. The curl of the electric field equals the change in magnetic field. Now we are left with the final equation. For this, let's consider this Maxwell's mechanical model. Trust me, this is the last one. In the center, we have an electric current. The electric current forces the vortices to rotate as an infinite series of vortex rings about the wire. Correctly, the magnetic field lines form circular loops about the current. This gives us the following relationship. Curl of the magnetic field is proportional to the change in the electric field. Again, using these mechanical models, Maxwell introduced a correction term called displacement current, which gives us the final equation. Curl of the magnetic field equals the change in the electric field plus a current density. These molecular vortices were modeled to be elastic objects whose disturbances could be computed. It was then a straightforward calculation, and to his amazement, the velocity turned out to be equal to the speed of light. In a single stroke, then electricity, magnetism, and light were unified. While Maxwell was greatly inspired by these mechanical models, over the years, he slowly started losing confidence in them. Finally, in 1865, at the age of 34, he presented a monumental paper titled A Dynamical Theory of the Electromagnetic Field, where he retreated from all the specifics of the molecular vortices model. Science historian Whittaker writes about this as follows. In this, the architecture of his system was displayed, stripped of the scaffolding by the aid of which it had been first erected. In this paper, the equations appear in their final form, quite independent of the means by which they had been established. The result was a dynamical theory of the electromagnetic field, which was still a mechanical theory, but abstract and general rather than concrete and pictorial. Electric and magnetic fields are abstractions that are not reducible to mechanical models. It is easy to see why this should be the case. The unit of electric field strength is the square root of a joule per cubic meter. There's no way we can imagine measuring directly the square root of a joule. We, with the advantage of hindsight, can clearly see that Maxwell's paper was one of the most significant scientific achievements of the 19th century, perhaps second only to Darwin's Origin of Species. However, for more than 20 years, his theory was largely ignored. Even Kelvin, who had worked closely with him before, found Maxwell's paper hard to understand. Maxwell's theory was just one of many theories of electromagnetism, and it was not clear what advantage it offered over Ampere's style. His complicated mechanical models made the matter even worse. There was also a second reason that Maxwell was absurdly modest. At a huge conference in 1870, Maxwell described his own theory as another theory of electricity which I prefer, downplaying its significance. Only after the discovery of electromagnetic waves by German physicist Heinrich Hertz, Maxwell's theory got widespread attention. Unfortunately, this only happened after his death. Sadly, he couldn't see the glory of his beautiful theory. It was the middle of the 19th century, and the heat engine was a hot topic. Scientists were working vigorously on explaining thermodynamics concepts such as pressure and temperature. One popular approach was the kinetic theory of gases, which predicted that molecules would have to move at extremely high speeds. But the scientists noticed a paradox. If gas molecules have such high speeds, why do we not immediately perceive the smell of an open perfume bottle at the other end of a room? Experience shows that it obviously takes some time for the fragrance to be noticed. German physicist Rudolf Clausius proposed that gas particles do not move freely but constantly collide with others, changing direction randomly. Because of this, particles delay the perfume's scent from being noticed immediately. In April 1859, Maxwell read Clausius's paper, and his imagination was immediately hooked. The sheer scale of the process was astounding. Maxwell himself put it this way: if you go 17 miles per minute and take a totally new course 1,700,000,000 times in a second, where will you be in an hour? In his calculations, Clausius assumed that all molecules travel at the same velocities. He knew this could not be precisely true, but could not think what else to do. Maxwell then took this task, studying what would happen if molecules had different velocities. However, it is not easy as there are billions of molecules, and deriving from Newton's law would be almost impossible. Maxwell realized that, instead, one would have to take the statistical approach, and that is how probability entered into fundamental physics. Maxwell made the following assumptions. 1. The diameter of the molecules is much smaller than the distance between them. 2. The collisions between molecules conserve energy. 3. The positions and velocities of the molecules are initially random. 4. The three components of velocity are statistically independent. Making these assumptions, he derived what is now called the Maxwell-Boltzmann distribution of molecular velocities. With this, one could then compute the probability that a molecule chosen at random would have a particular velocity. Maxwell distribution is a probability distribution. So, the height doesn't correspond to the number of particles. Instead, the area under the curve gives the number of particles in the respective speed range. For example, here is the distribution under different temperatures. Raising the temperature causes the curve to skew to the right, increasing the most probable velocity. However, the area under the curve remains unchanged, since they are all probability distribution curves. This new theory of Maxwell predicted something that seemed to defy common sense. In particular, it predicted that gas viscosity is independent of its pressure. Viscosity can be thought of as the internal friction of a gas that causes drag on a body that moves through it. One might expect that a more compressed gas exerts more significant drag, but Maxwell's theory predicted otherwise. Even Maxwell himself was surprised. A few years later, Maxwell and his wife Catherine attempted to do the experiment themselves in the attic of their house. Catherine's main work for these experiments involved keeping a fire continuously stoked for hours to produce steam from a kettle and so maintain a constant temperature for the gases whose viscosity Maxwell was measuring. Together they showed that Maxwell's prediction was correct, and that viscosity doesn't depend on pressure. Maxwell did recognize his wife Catherine's contribution. He wrote to his friend Peter Tate in his usual humorous style, "My better half, who did all the work, is involved in other research. When she is done, I will let you know her answer to your inquiry." The inquiry was about experimental data. This was Maxwell's first venture into the gas theory, and it was a banger. His work drew admiration, particularly from continental scientists such as Clausius and Kirchhoff. But even these admirers failed to see the full significance of what Maxwell had done. But there was a young man in Vienna who did. His name was Ludwig Boltzmann. Boltzmann was so inspired that he spent much of his long and distinguished career developing the subject. With his groundbreaking work in gas theory and electromagnetism, it is rightfully justified that Maxwell is the greatest physicist, just after Newton and Einstein. But he did so many other works which we will highlight now. Using prisms, Isaac Newton demonstrated that white light, such as sunlight, comprises many monochromatic components. However, obtaining a particular color with a combination of other colors was still open. Maxwell demonstrated using a colored top that any natural color could be produced from the three primary colors: red, green, and blue. Most of this work was not particularly new, but Maxwell's technique of using linear algebra for color combination was quite novel. These methods are still used. Interestingly, Maxwell was the first person in history to produce the first color photograph. He displayed the picture of a Scottish tartan ribbon at a lecture on his color investigations at the Royal Institute in May 1861. Although very clever, Maxwell's work on color theory was probably some of his least astonishing work. However, it was easier for his contemporaries to understand and received more recognition than some of his other works. In 1867, Maxwell proposed a thought experiment called Maxwell Demon, showing that the law of thermodynamics might be paradoxical. The second law of thermodynamics says that when two bodies of different temperatures are brought into contact, they attain the same temperature after a certain time. Maxwell's thought experiment challenges this. A hypothetical demon controls a door between two chambers containing gas. As the molecules approach the door, the demon quickly opens and closes the door, allowing only fast-moving molecules to pass through in one direction. This causes one chamber to warm up and the other to cool down, thus decreasing total entropy without applying any work. This violates the second law of thermodynamics. The thought experiment first appeared in a letter Maxwell wrote to his friend Peter Tate. Still today, the matter is not resolved and provokes significant debates in the philosophy of science and theoretical physics. One of Maxwell's last great contributions to science was his establishment of the Cavendish Laboratory. Maxwell was put in charge of the development of the Cavendish Laboratory. He supervised every step in the progress of the building and purchasing scientific apparatus. As of now, more than 30 Cavendish researchers have won Nobel Prizes, and the electron, neutron, and DNA structures were discovered here. While working at the laboratory, Maxwell started to get sick and died of abdominal cancer on the 5th of November 1879 at the age of 48. It is clear that Maxwell was an excellent scientist, admired by many of his colleagues, and responsible for many great works. His masterpiece, Treatise on Electricity and Magnetism, revolutionized our physical world, without which the world would not be as it is today. Maxwell was no longer living when his work became truly famous. People know about Newton and Einstein because they ensured they knew what they were responsible for. This was not in Maxwell's character, for Maxwell was just a quiet, modest man who took great joy in his work and did not need fame and the appreciation of others to give him satisfaction in what he had achieved.